Thank you for the really interesting talks. So we can start the Q&A session now. So there have been several questions posted on the Whova Q&A panel. Please feel free to keep posting questions. What I'll do is I'll go through and ask the questions that haven't already been answered. Some of the questions are directed to a specific paper. Some of them can be more general, and we can ask all the panelists to comment on this. I'll leave the last part of this session in case people would like, attendees would like to raise their hand and actually speak and raise some discussion points. So the first question is for the limp motion paper. And it's asking, how did you calculate the point cloud using one IMU on the wrist?
Hello. Hello. Hello.
Hello, we can hear you.
Yes. For that question, calculate the point cloud is a offline state. Yes, we calculate a very big point cloud, and the the inside of the point cloud. It means we can use one MU and its readings to calculate the orientation of the rat, and after that, one rat orientation can derive many possible elbow orientations, and these orientations, if we have the user's arm length, we derive the point cloud, which means 3D locations of these joints. That's my answer. Thank you.
Sorry, I'm asking, that's my question actually. So I don't follow up on that. So yes, like you use IMU on the wrist to get a point cloud, but in order to use orientation of the wrist to get a point cloud, you need body direction, right? So you mentioned arm track in your paper. Arm track actually use opportunistic sensing. Also, they estimate body direction only when your arm falling down, so you can get a body direction. So that means if your body keep moving, so you may miss that part. Did you get a chance to explore that part? So how do you get body direction to calculate the point cloud?
Your question is about the facing direction, right? The facing direction.
Yes.
Yes, we assume that if the facing direction changes, if the user's location changes, as I claimed, we have an edge device in the surrounding. We use an edge device, nearby edge device, and if the user's location or facing direction change, we need to initialize limb motion again. We can process the problem. Yes. Thank you.
Thank you. So the next question is for the digging deeper paper. So you mentioned that you choose these data sets because they match in the sampling rate, etc. Does that mean transfer learning would fail with different sampling rates? Did you investigate?
Thank you very much for the question. We did not investigate this in this particular work, but I would expect that it would not fail, but at least we can expect a drop in the classification results comparing to data sets that share the sampling rate.
Thank you. Next, I have a general question for all the panelists. So this was posed by another panelist. Basically, the papers supervised versus unsupervised are about 50-50. Could your problem be reframed differently, or is it mainly constrained to the problem observed and data explored? I think that was a question from Flora. Does anyone have comments?
I guess I can take it for ThinkWise. I mean, we're synchronizing across multiple sensing modalities. And so the idea here would be that if you were to label data in one sensing modality, that you can also transfer that label to another sensor modality. But to do that, you need to align the sensor signals. And so I guess whether it's supervised in the sense that there are labels or not, doesn't necessarily, might not necessarily apply in our problem. However, one factor could be that if labeling in one sensing modality can be a lot easier, right, than labeling in another sensor modality. So I can automate the detection of, say, objects in a video sensor stream a little bit better than than looking at an accelerometer signal. And so labels from one, leveraging this notion of automated labeling being easier in one sensor stream can then be transferred over to another sensor stream. So whether it's supervised or unsupervised, we can sort of handle, I guess, both scenarios. I hope that answers your question. ThinkWise.
Yeah, I also like to point to our paper, Espresso, segmentation on multivariate time series data. And the main purpose of the segmentation can be when we don't know the labels and we have lots of input data from different modality, then and we don't have any background about the data, we can do some kind of unsupervised segmentation to extract some insights about the data. Here in our paper, we evaluated segmentation on different types of data set like emotions, hand gestures, eyes, blinking states, and human activity, human physical activities. And I think we can this segmentation can address in both supervised and unsupervised methods can be helpful.
So can I go? So for IME2 paper, we think that there are a lot of activities in the wild, such as dangerous workplaces, that are actually hard to record because of privacy or practical reasons. So that the idea of IME2 is that such data sets like rescue places, you can collect those data in YouTube, right? People have recordings from their cell phones or stuff. So if more computer vision and signal processing and activity recognition people jump into this pipeline to get more diverse data from YouTube, and then convert it to real world by training a model, I think it can be a good opportunity to virtually expand the class of activities and variations within the activities beyond what we can collect in the wild for now.
That actually relates to a question I wanted to ask the IMU2 paper. So some human activity recognition is related to health, sensing health activities, and how would your work and your idea sort of apply there?
Yeah, most recently, the health-related based on wearables are using biosensors, right? Likewise, smoking detection works recently using this heart rate or things like that. But then it is unclear how human motion changes can relate it to those biosignals. But at least for health conditions that involves this motionless, gait, movement. I think if we can collect such data sets just by using videos, and then we can translate those motion signals into real world by training a model, I think we can accomplish that. But then those most of those health conditions related motion signals are very subtle, that computer vision technology might yet to be captured reliably. So we have to come up with some better engineering ideas to accomplish that. That's what I think.
Thank you. Someone has raised their hand as an attendee, so we're gonna give them access to the microphone to ask their question.
Oh, thank you very much. I'm going to ask a question in my own field as I'm doing the factory works. So in fact, there are lots of managers in the factories. They don't want to label data or training data actually, as they have real benefit for their work. So in other words, we are now trying our best to prevent those additional process to get our results. Like in our case, we are doing some data that has very obvious patterns to be discovered. So I think using the unsupervised learning, it's suitable. I think it's more suitable for us to get the results without a lot of effort. And that's also my reason to continually do the unsupervised in the factory fields. Obviously, we can get better results from the supervised learning, and we can also get benefits from the unsupervised field. Thank you very much.
Thank you. So I have one more general question for the panel. So current data collection protocols involve recording under lab conditions. What would good strategies be for truly large scale data collection?
Can I take, I'm happy to take this question. So I think the simple answer is just spend more money on, right? Get an industry partner, spend more money on it, that's easier, but that's not realistic. So realistic speaking, as a researcher, I think there are different ways you can do that. First, why is collecting data in large is so hard? Because there is not enough easy enough devices you can capture enough data. For example, if you want to capture human body posture, right now a lot of data set collected by vision, cameras, but it's hard for people to carry data things. So one thing we can do is lower the barriers of data collection. What if your smartwatch or one single device can capture all the information needed? So that makes things much easier. So that's make it more advanced in that direction. The other one I would say is being creative on how to get data sets, right? So that's why I like the IMU2 paper, because we can actually be creative and borrow data set already collected from other area and also use that data set on this part. So that is another way. And you can also use a GAN network to generate fake data to help you to scale up your data sets.
May I answer this question from another viewpoint? Yes, I think in current supervised data sets are very specific. For example, human activity recognitions focus on physical activities, or emotion data sets focus on emotion data. But when it comes to a real data set, we could have a very large amount of data from different sensors, different modality, and we should care about all these sensors together simultaneously. So current approach usually focus on specific tasks like physical activity recognitions. And when we want to combine all these different tasks together, for example, in smart homes, or there are many examples for this. Then we need to care about all different modalities. They changes frequently, and we will have lots of null classes. I mean, transitions between tasks, between classes, and we need to capture the relation between changes in this different sensors. So I think we need some tools, we need some techniques to find the relation between a large volume of data, large volume of sensors, and in online. Yeah, that was my viewpoint. If we want to capture real data set, then we need specific tools to find, to cluster or to find to do some fine-grained groups in the sensors. Thank you.
Do any other panelists have comments about the last general question? About truly large-scale data collection?
Yeah, so Katyn, this is Nabil Al-Shrafa from Northwestern. I think that's an excellent question, because a lot of the work we do is connected with health and trying to understand and scale a lot of what we learn from samples to the general population. I get asked this question quite a bit, right? Aside from, when it comes to wearables, right, aside from dealing with burden, privacy, and comfort, right, when it comes to these wearable devices, I think there's just a huge culture issue as well, right, in terms of dealing with different collaborators. So I remember working with a nutritionist, and I asked her one time, why don't you use Fitbit to collect physical activity? She was still using self-report. And one thing she told me was, obviously there's that notion of, how do we deal with missingness of data? How do you deal with poor quality data? So a lot of, when it comes to sort of the self-report measures, there are standardized approaches to dealing with a lot of these issues. And yet, while we're building them in the human activity recognition field, this is definitely an area standardizing our approach to how we apply different machine learning models, and also how we handle missingness of data and poor quality data is really important for us to be able to convince communities to use these devices at a large scale. And this is not to say there's a lot of excitement in this area too, and a lot of collaborators willing to collaborate and innovate in this area.
Thank you. So we now have several of the attendees have raised their hands based on the discussion we've been having. So I'd like to give them an opportunity to speak. The first is Nazmun Nahid. Your microphone is muted. Okay. It seems that there's a difficulty with his microphone. So let's, the next person is Atikur Ahad.
Hello. Yes, thank you for a good number of excellent works. So we are working on rehabilitation data analysis for the stroke patients in hospitals. So what we are facing, that from the video we get skeleton data, and from that data we want to differentiate the subtle, very little movements from last week and next week and next week, the progress. So rehabilitation patients, their progress is not so much. So from the skeleton data, we cannot get enough information or cannot get the differences. Is there any possibilities that sensors can help? Or, what kind of sensors can be used? I mean, patients, they don't like to use sensors. So any idea whether skeleton data can be used in a different way or something like this? Any comment on that? Because this is related to, very important research work, but we cannot progress. Thank you so much. Anyone?
Answer.
Oh, I'm happy to take in this one. So I think your question is for stroke patients, their progress very slow. So their posture, you're trying to measure the change is very subtle. So what kind of sensor you can use to actually capture those subtle changes on the patient? Is that right?
Exactly, yeah.
Okay. So unfortunately, based on my knowledge, it's hard to do that in the wild, because current technology, in order to accurately track those things, you have to put multiple sensors on the body to accurately measure that. So there's no devices. They're called multiple sensors. It's not comfortable and also can be consume a lot of battery. So it's not, at this moment, based on my limited knowledge, I think it's pretty hard to do that. My lab is working on some new technology which can use very practical form factor to do more and more accurately, but it's ongoing, haven't been published yet. But at this moment, there's no simple commodity devices can measure detailed, subtle body posture changes.
Yes, thank you. Such one related point that came, that we are working in a hospital environment, fixed environment. So it's not that much wild and very selective movements based on the therapist. And we are using Kinect sensors to extract the skeleton points, because the patient's impossible basically to use any kind of sensors. And also we are not sure that whether any kind of accelerometer or gyroscope data can be suitable. Based on our research, I don't think that this is that much helpful to get subtle differences. So if anyone has any idea, or we can discuss in future as well, because this is very important work for the future of the stroke patients or this kind of hospital or elderly people's movements progress. We want to see that how far the progress is going on based on the therapies or exercises of the stroke patients. And they have one side is disabled, but another side is okay. So we need to check. And walking patterns at the same time, we cannot get any paper so far which can help much. Thank you.
Thank you for your question. There's another question directed at the IM YouTube paper. So regarding the pipeline, when going through the 2D pose estimation, the 2 to 3D conversion, the 3D motion to IMU data generation, will there be much accumulated error?
Thank you for the question. Yes, because individual problems listed are not solved yet in computer vision community. So there can be a lot of errors. But the opportunity is that we have unlimited amount of data from the YouTube. So what we do is, between the modules, when we pass 2D pose to 3D pose, and then 3D pose to calibration and ego motion estimations, we basically try to find out most inconsistent frame, such as most erroneous frame, and we just drop those. We just remove those, and we just trying to collect as high quality possible data as a training set, so that if we need more, we just can go grab more data from online. So yes, there is accumulated errors, and we have to check that.
Thank you. I believe there's one more attendee who's raised their hand, so Yu Guan.
Hello, can you hear me?
Yes.
Hello?
Hello, we can hear you.
Oh, I can't hear you. But if you can hear me, that's fine. This is that's fine because I'm asking questions. Well, this is a reply to the stroke rehabilitation problem. We done similar things. All you need to do is to get 2 accelerometer on both wrists, because for stroke rehabilitation patient, they get paralyzed side and the non-paralyzed side. So you know they're imbalanced, and through extract features and you know and do feature engineering. For example, use a ratio from both sides, and then you can measure the rehabilitation. If you want to know more, you can contact me, and I can send you some papers.
Thank you.
Yeah, all done. Thanks.
So there's another directed question at the Digging Deeper paper. So it says, there has been work using a transformation matrix to normalize orientation in point clouds. Is this an example of an area where the network can normalize automatically? And if so, why does that work here?
Actually, I don't understand that question. Maybe Christoph, you can help me out here.
I also didn't really get the question, to be honest, but I think this is one of the problems I think in transfer learning when you work with IMU data. The IMU data is really unstructured in all the data sets. So basically transforming it from one domain to the other also means that you really have to understand what the sensor looks like. And doing that usually means that you lose information on the way. I think this is a problem that we're all bumping against at the moment.
Thank you. Hopefully that answers the question. If not, please raise your hand. We have another person who's raised their hand, Daniel, if you want to ask your question.
Can people hear me?
Yeah, we can hear you.
All right. No, I was the one who asked the question about digging deeper. Yeah, it's a bit complicated. Let's see if I can explain a bit better. So basically, the PointNet paper, which came out a while ago, was able to just take in an unordered set of points and in a point cloud and make classifications and segmentation information off of it. And it was able to, basically take in the points and make it so that it was kind of agnostic to the order in which the points were in. It used a couple layers in the network, which acted as sort of a normalization function, where it kind of normalized the input to a specific orientation. So as in, if you put in if the points looked like a coffee mug, if you put them in, it would sort of normalize it to a fixed orientation, say with the handle on the left upright. And it seems, and that is really helpful for getting it working, because otherwise the system would not have worked. But it seems like here, sort of orientation normalization doesn't seem to do anything. And so I'm wondering if there's a reason why that's the case here, because it doesn't seem to be a general thing for motion, for trying to make classifications based on data that has definite important spatial orientations, but which can still be rotated to non-canonical orientations.
Right, and I think that is the exact. I mean, you basically said or basically gave the answer already. I think we are not talking about mugs here. We're talking about time series, where the orientation is really important. If somebody moves this way or moves that way, it's completely different. So therefore, we really want to learn this in our models. If we can't, if the sensor is changing the orientation, then you have a problem. So I think this needs to be modeled somehow. And if we don't know this, or if it's while transfer learning, forget about this somehow, then I think there is definitely an error being built in there that we cannot fix anymore afterwards.
Okay, thank you.
Thank you. I believe two of the panelists have raised their hands. So maybe Nick, did you want to ask your question or say something?
Sure, just following up on the question about transfer learning, that paper is pretty interesting. I was just wondering if either author might want to comment on what they found or thought was specific about trying to do transfer learning in some IMU type of situations. So we see transfer learning working pretty well in images and audio in different cases and so on. So yeah, what are some of the specific problems they found for doing this? Well, you mentioned this time series already, but I was wondering if you might elaborate some of those challenges.
Shall I start? Okay. So basically, I think the outset of this paper was that we wanted to actually see whether we could reproduce indeed the successes from computer vision, because their transfer learning really works well. And what Thomas Plott yesterday already said in one of the other activity recognition sessions, of course, applies here. The data sets are extremely small. And on top of that, the data is not just images. I mean, cameras, produce similar type of data. Inertial sensors are very, very diverse. It's not just the sampling rate, it's also the sensitivity, it's the orientation, where on the body they're attached. So all of these things matter somehow. And that makes, I think, the classification problem of activity recognition really hard. But it also makes transfer learning even harder, I think. And what we were trying to show in this paper was if we at least know what type of sensors are being used, where on the body, with which parameters, and if we try to really match that, we probably have really good results. The surprising part is that we don't, and we don't really know why. We tried all permutations, including the right one, and that one is not really standing out as the better one, which I think is very surprising.
One result that maybe was not pointed out during the video is that we got good result or better results when we, for example, trained on the right hand and transferred to the left hand, but in the same data set. But this does not apply if we transfer between data sets.
Thank you.
It's really interesting. Thanks.
Yeah. So I think our last question will be Tuo Chao. You've raised your hand.
Yeah, thank you. Yeah, I have one question for the IMTube, the papers. Yeah, so as you mentioned, you have two kinds of the data. The first is video from the YouTube, and then you just extract the 3D pose from the YouTube videos. And another part is just the IMU data. So, so what you do just for my when I listening to your presentation, I just know that you will use the 3D pose from the video YouTube videos to generate the virtual IMU data. Is that right? Yeah.
To answer, thank you for the question. So the goal of IMTube is to generate virtual IMU data to tackle this sparse data problem in our community, right? To expand to a lot of activities. So we do estimate 3D pose, but the body frame, we use forward kinematics, how the body center moves to the actual sensor target, for example, wrist, so that we estimate the sensor coordinate in local, and then we track those IMU movements. And another part I want to mention is that not just the sensor movement to estimate accelerometer or gyroscope, we are actually using a module that named IMU-SIM, which is developed by sensor and biomechanical community to simulate MEMS noise and characteristics that real sensors have. So we actually apply that technique onto the sensor locations to generate the most realistic data, which is possible. And in our experiments in our paper, by additionally calibrating the sensor data, we could actually train a model that could classify the real IMU data up to 80 or 90% according to activity.
Yeah, so my question is that, so if I do this, if let me do this project, I will just think very naturally that's so there are another way. So because your way just to use 3D pose to generate the virtual IMU data, and another way just an inverse process, just using the real IMU data to generate the 3D skeleton. And yeah, so why you choose your method? So have you just think of the method I just mentioned that use the real IMU data to generate the point cloud of the 3D pose? and then just use this and the 3D pose from YouTube to just put this, just compare this, not compare, just one for training and one for testing. So why you generate the virtual IMU data? Yeah, I'm very curious.
So I think the question is, how could you evaluate the quality of 3D pose from your IMU2 pipeline? And so yes, so because the data, the video is from YouTube, such that we don't have ground truth 3D pose measured, right? So to have more a detailed evaluation in sample level precision, we were using another data set named Total Capture from graphics and vision community, which actually has time synced video and wearables. So that we in our paper, we also go through the sample level motions for locomotion activity to actually see the quality of the generated virtual data. But as I mentioned for other questions today, that we're trying to only keep those with high quality virtual sensors. That does make sense by using this temporal smoothness constraint to filter out those abrupt changes in motion, which is unrealistic. And we actually we could show that, for example, this hand moving motions in the wrist was actually well reconstructed by virtual IMU data compared to real ones. So, and then that's actually a good point that there is another in graphics community from there is a paper generating 3D motion capture using 6 different on-body sensors, the IMU data. So it may be a good evaluation how much those can compare to the 3D motion captured from the YouTube video.
Okay, thank you.
Great. Thank you, everyone. We'll have to wrap up the session now. We've gone over time a little bit. Thank you to all the authors. I know there's still some questions that are remaining that we didn't have a chance to get to, so please continue to post them on the Whova session Q&A panel. And authors, please have keep an eye open for questions. Thank you, everyone, for joining, and especially to the student volunteers for helping. Bye.
Thank you. Bye.
Thank you.
Thanks. Bye-bye.
Thank you.